they get the wrong propagator. Actually, Kuka showed that. The wrong propagator for the single particle system or single particle state. This basically means that the particle is not moving in time or space, which it should be like this, but they get it like that. So that's a problem. Another thing is that for them, because they construct these clocks and variables out of usually, I mean, in the sense that non-Dirac observables, so these don't commute with your Hamiltonian. So the action of them just throws you out of the constraint surface. So you have a problem with that too. Now, we're going to solve these problems in our framework in one go with two new assumptions. So this is the modified version. So it started 2001 basically and 2009, and now we are improving it this year. One of the improvements on this is that we use evolving constants of motion instead of whatever Page and Wouters used, like the spin and other stuff. So evolving constants of motion are basically Dirac observables, which are parameterized by that small t that you saw in, like we call it time. That's the weird name, evolving constants, because they're actually constants. Their gauge transformation is 0, but they kind of move because they have a t in them. This is what we have actually in our new work. We now consider interacting clock and the system, and that means that they don't commute. So because I have 5 minutes, I have to go faster. So it means that now our probability, first of all, it has an So it has an integral over dt, because these are now evolving constants of motion. This projector corresponds to evolving constant. They have t in them, but we don't know where does that capital T becomes equal to capital T naught. So we have to integrate over the whole range of this experiment, basically what you are doing, and then ask this question that you saw. So what if t takes the value of t naught, does the system has q equal to q naught? And the numerator is now different from all previous works because these don't commute. But so these two new things remedy the problems of the Page-Wouters system. So I'm going to quickly go through our model. This is a cosmological model with two scalar fields. The Hamiltonian constraint, which is a constraint, becomes like that. And these are the canonical variables in the gravitational sector related to the scale factor. And this is the momentum of the scalar field. And so first step, you find the Dirac observables. Immediately, based on equations of motion, you see that P phi commutes with the Hamiltonian, which is the only first-class constraint in the system. So this P phi 1, and P phi 2 are Dirac observables. Out of those, so we can create a nice four-dimensional phase space based on these observables. And then we identify a combination of the phase space with that T. And then we go on and construct two evolving constants of motion. As you see, both of these commute with the Hamiltonian, but they have t in them. Well, here you see these. And that's why they're called evolving constants of motion. And so then you go on and quantize. So for now, we are doing just a Schrodinger representation, no loopy stuff, no nothing, because it's already very complicated. The self-adjointness is very important because, remember, we want observables. If they are not self-adjoint, they are not observable. Even if you don't look for observables, if they are not self-adjoint, you will have problem with defining probabilities. Okay, so I'm going to pass. So the way we assure that these are self-adjoint is via deficiency indices, which I don't talk about because there's no time. Maybe if there are questions at the end. So now what the probability? So what we do is that our clock, so this thing, has discrete eigenvalues. We chose it like that. However, the other variable, E2, which we want to compare with respect to clock, previously it was called Q. Now it's called E2. It has continuous spectrum, so we look in, so basically we are looking if E2 goes from E21, which is the central value of E2 minus some delta, small delta E2 to plus delta E2, basically. For the density operator, we choose a pure state, but you see these Heaviside functions. These two limit the system where O1 and O2, so this is a function of O1 and O2. This is between O11 and O22. So basically, in the phase space, you have in configuration space, you have a box, and you put your state in that box. This is an idealization, of course. And so at the end, what happens is that you can compute the denominator as that you saw before. This denominator, you can, for now, we can compute it exactly. However, the numerator is a tricky object. Well, it's still under construction, and we hope that we can compute it exactly. For the moment, we did certain approximations. So basically, to understand what's the problem, we have these integrals of exponentials of tangent hyperbolic inverse of sine and cosine, something like that. So we have to go on and compute those integrals exactly. Anyway, so this is a very preliminary result. And so this is E2. This is time, the clock, and this is the probability. So as you see, the probability is kind of peaked around some values. And as time goes on, this value of E2 goes to the right. So this is the approximation in the classical regime. Basically, we could do it in that. And basically matches with the cosmology. So the volume of the universe is changing and increasing with this clock. Now, if we can do the integrals exactly and correctly, we will see more stuff close to where the quantum regime is strong. And then the next step is basically to go on and do the either polymer quantization or loop quantization. So I'll summarize. So for a solution to the problem of time, one of the best ones, in my opinion, is the conditional probability. And what we construct is now free of those issues that Page and Wouters proposed almost 40 years ago. And this is realistic because our system and clock are both quantum, both observable, and both, interact with each other. So this part, especially of interaction, was not present in any of the previous works. And so this model also, I didn't talk about this obviously because of the time, but incorporates collapse, kind of an explanation also for the collapse due to decoherence. So it has other ramifications. And so the paper comes out soon, hopefully in a month. And yeah, so thank you very much.
Okay, so thank you, Said. We have time for a few questions. Actually, I had one about your second point. Maybe you went a bit fast. So you didn't explain how you got the right propagator, let's say.
Yeah, I didn't explain it, but the point actually is that the reason you get the right propagator is that you use observables or evolving constants of motion as for your Q's and T's for your projectors. Page and Wouters didn't do that. They just took something we call partial observables in this context. So they are not Dirac observables, and that's why they didn't get the correct result.
Oh, okay, thanks. Yes.
Yeah, I had a related question. The plot you showed, is it correct with respect to semi-classical limiter? Instead of checking the propagator, you could check that the speed of this wave packet is what you would expect classically.
The plot?
Yeah, you said it's moving to the right.
Yes.
So is the speed consistent with the classical equations?
Yes. So what we did was in the classical regime, we computed. So we have a formula. We have a formula for E2 as a function of small t, and E1 as a function of small t. You eliminate t between them, and you find the classical E2 as a function of E1. Compared to this, in the very classical regime, they actually match. So this is that regime. Yes. That's the approximation we did actually.
Okay, good. So I think we have to move on. Let's thank Said again.
Can you hear me? Maybe better here.
Okay. So our next speaker is Andreas Pittis, who's going to tell us about, towards the phase structure of first-order Lorentzian-Palatini quantum gravity via groove field theory.
Okay, thanks for the introduction. Thanks to the organizers for this nice conference and the opportunity to talk here. So this talk connects with Daniele's presentation on group field theory as a quantum field theory of space-time, so chunks of space-time, GFT quanta, playing together and hopefully come together in a way that the continuum emerges. And it also connects then with Luca's talk right afterwards, who looks at the cosmological perturbations in this context. So you know that group field theories are more complicated than matrix models. They are addressed with additional data, group theoretic data, essentially Lorentz group data. And because they're field theories, we would like to analyze their phase structure and hope, let's say, that some phase corresponds to a nice continuum geometry. And the idea is basically to employ Landau-Ginzburg mean field theory, which is a very simple tool that we all know from kindergarten, to inform ourselves about the phase structure of such models. And in particular of this model here, the Barry-Crane model, in fact. Okay. So the outline is I will talk a little bit about the Barry-Crane model as a model for Lorentzian Palatini gravity in first order formulation, and then come to the Landau-Ginzburg analysis of this, and then I will conclude. So this model, the Barry-Crane model, is a model for 4D Lorentzian quantum gravity. The gravitational theory that we are dealing with is Lorentzian Palatini gravity in first order formulation. The quantization technique that we are employing is that of a lattice path integral. Now at the classical level, how do you get to this theory of gravity? You get it by means of BF theory plus constraints, simplicity constraints. At the quantum level, when we look at it from the GFT perspective, we look at the GFT quantization of BF theory and impose simplicity constraints at the level of the quantum theory. So what is Landau-Ginzburg theory? Okay, I hope we all remember what we can do with it. Describe first and second order phase transition in a very coarse account. So basically we're trying to evaluate the partition function, which is sometimes analytically possible, but mostly not. So we have to resort to numerical techniques if we want to do it fully. But Landau-Ginzburg theory provides the means to do it coarsely or approximately. Yeah? So that is the idea. We want to employ this to our funky group field theory models to get an idea of the phase structure. And the idea is that if we can find a phase transition to a condensate phase, which is highly occupied by quanta, and here then quanta of geometry, is that this is a good step towards understanding the continuum limit in group field theory. Oh. So as I said, group field theories are field theories, so we want to employ field theoretic means to analyze the phase structure. Want to understand phase transitions therein and see if a non-perturbative vacuum can exist with the tentative continuum geometric interpretation. And that is also of relevance for spin-form models and simplicial gravity formulations, because you can basically have the expansion of a group field theory partition function is a sum over the amplitudes of spin-form models. And you can rewrite also these amplitudes in terms of bivector variables, and then you get into the reign of simplicial gravity. So let's go back here to classical BF theory and then the quantization thereof in the continuum, which gives you spurious formulation. So what you want to do is you want to quantize this on a lattice. So you would expand this thing here, the delta distribution in terms of characters. Then you have to add your lattice, and the whole construction gets then support on this lattice. So a way to do this, another way is by means of the Oguri model. So you introduce this field with this invariance property, which when you go to the Lie algebra formulation, so where G is this Lie group that I spoke of, you see that the variables dual, so these flux variables, they sum up and give 0, so the field has the interpretation of a tetrahedron. So then you need this funny interaction term, which has the combinatorics of a 4-simplex. And then you understand that you can generate, when you have the partition function here, you can generate amplitudes, which are actually, the graphs are dual to triangulations. And yeah, this is not so important, it's just an extra development of the last 10 years. So how do you bring in gravity there? At the classical level, you introduce another term here to the BF action. G is SO2C. Then you vary with respect to mu, and you try to establish in this way a relation between the B fields and the tetrads. So that's the way how the metric information comes into the game. And then you solve it, you put it into the action, you see that you get this action here for Palatini gravity in first order formulation. So basically you have promoted the connection and the field that has here the metric information, the tetrad, to two fundamental variables. Okay, so now how do you do this at the level of GFT? So you have your tetrahedron field, you add another slot here, and this is basically a normal, either a time-like, light-like, or space-like normal. And the idea is basically that first you have the same closure condition that I spoke about before, but then you have, when you play around with each of these group variable slots, you have to play also around with like covariantly with the normal. And then you want to impose simplicity at the level of the quantum theory, okay? And basically these U's here, U1, U2, U3, U4, these are the stabilizer groups of this normal. Okay, so for instance, if you have a time-like normal, then what is the operation you can apply to it so that it remains invariant? It's basically a rotation. So you want the whole field with its geometric information encoded in these G's be invariant with respect to SU2 information. So you average this out. And if you do this, for instance, for this case with a time-like normal, what remains is basically data. This is basically SL2C modulus SU2. So you have, in that case, 4 copies of the 3 hyperboloid. And then the normal is also living in the 3 hyperboloid space. So this is just an example. You can play the game also for the space-like normals and the time-like normals. And the idea is basically that in this way you have tetrahedra with the space-like, time-like, and light-like signature. Because in the end, what you want to do is, with your theory here, with your 4-simplex, you would like to generate in perturbative expansion, or maybe then when you look at the non-perturbative sector, a Lorentzian manifold in the continuum limit. So what we did with Alex and Daniela, and we looked at all sorts of interactions here and so on, and in the end one has to exclude stuff because you cannot probably put arbitrarily all types of tetrahedra together that you want, in case you want to have a nice local causal structure in the 4-simplex. But in principle, we have the tools ready to further develop this model. So now we have this model. Let's look at the phase structure of this from the point of view of Landau-Ginzburg theory. So in order to do this, we need to introduce a scale, basically the coarse-graining scale, and that comes by adding a Laplace-Beltrami operator here into the kinetic term, okay? And then we restrict it to the case where the tetrahedra are all only space-like. So as I said, all of these slots live in the 3 hyperboloid. So then you proceed in a standard way as you do for Landau-Ginzburg theory for ordinary field theory, local field theories. You do it now here. GFTs are non-local, it makes it a little bit more difficult, and also you're dealing with the infinite dimensional representation theory of SL2C to do your computations, because basically you're trying to find the correlation function from the setup here. You find the non-trivial minimizers, and then basically you have a background, which is your non-trivial minimizer, and you look at perturbations around it. And you put this into your equation of motion, you solve the equation of motion, and you get the correlation function. And then from the exponential decay behavior of this, you determine the correlation length. This is now the correlation length on the space of geometry, so to say. And then there's a nice thing about Landau-Ginzburg theory. You can look at the domain of validity of Landau-Ginzburg mean field theory by means of this quantity which Ginzburg gave to us. Basically, it quantifies the strength of the fluctuations. So if the fluctuations become too big, then the whole setup breaks down, because we are looking at linear perturbations over this background. So if Q is small, this all is good. If Q blows up, we are in trouble, and we have to look at non-perturbative techniques. Okay, so you can employ this now. Just as a comparison, for local scalar field theory quartic, you get this result here. And basically, this exponential suppression factor comes from the hyperbolicity of the 3 hyperboloid. And basically, it means that the critical dimension is infinite. Yeah? And it means also that the mean field theory is always applicable and gives a good account of the phase transition. Now, you can do this for the Barry-Crane model and for this quintic interaction, but also for other types of interaction, derived interactions, so to say. You get this expression here, which also encodes the combinatorics. And you can generalize this to arbitrary interactions. So all of this is nice, and you see that basically because of the hyperbolicity of the Lorentz group, that the fluctuations are suppressed, and basically we can use mean field theory to study the phase structure of this model. And yeah, so let me summarize. So I gave you a quick snapshot of this Barry-Crane model as a model for Lorentzian quantum gravity with all types of causal building blocks, which had not been, so to say, previously given. And then how to analyze its phase structure using Landau-Ginzburg mean field theory. And in spite of the non-locality of group field theory, you can also apply the method there. We see that there is a condensate phase, which is the transitional to which is describable by means of mean field theory. And so just in context with this idea of a continuum limit, well, this non-perturbative vacuum is highly occupied and is, let's say, a good candidate state to describe a continuum geometry in this context. And it's a nice thing in the end also because, as Daniele said, well, these condensate states appear to have like a Friedmann-like relational evolution. So, and the hypothesis behind this condensate cosmology approach was always that there is a condensate phase. Now we see that really it is there, and the crucial feature to get it is coming in through the Lorentz group. So, well, there are a few things one can do in the future, but I think I don't have to run over the time too much. Yeah. Thank you.
Thank you, Andreas. So, questions?
I was wondering whether really the Landau-Ginzburg model is the best, especially in the case of gravity, because in already from solid state physics, we know that there are some phases beyond the Landau paradigm, and that are, and especially like topology and topological excitations and such things become relevant. And in gravity, these are especially very important features. So I was wondering whether maybe this is not the luckiest choice of, the phase transition analysis.
I mean, we have also worked with functional renormalization to look at the non-perturb, because I mean, essentially, okay, we try to compute Z with the Landau method, and we are expanding basically around this non-perturbative vacuum, look at the fluctuation behavior around that. So it's kind of non-perturbative also. And of course, if you really want to look at full non-perturbative feature, you would go to functional renormalization. We have not done this for this model yet, because it's technically very involved, but we've started looking at that. So, but the strange thing is, of course, this exponential suppression, because of the Lorentz group, is killing all the fluctuations. So it could very well be that at the level of the functional renormalization group, we see that the anomalous dimension is 0. So the tree-level theory is all we need, which is a bit puzzling. We have to understand this better. It also has to do with, do we understand the renormalization group or this coarse graining scale well enough? You know, because this is a renormalization scale on the space of geometries. We have to understand this notion better. Yeah, but we hope to get to questions as you ask.
Mm-hmm. Thank you. Okay, so let's thank Andreas again. Okay, so our next speaker is Luca Marchetti, who will tell us about scalar cosmological perturbations from full quantum gravity.
Okay, hello everybody. Thanks to the organizers for having me, and thanks to you all for being here, despite being the second to last talk of the conference and being the day after the conference dinner. So I do appreciate it. So yeah, I'm going to talk about scalar cosmological perturbations from full quantum gravity. And as you can imagine, it is not an easy task to... It doesn't work? Is it my fault? Oh, okay. That works. Okay. Yeah, so it's not an easy task to extract cosmological perturbations from full quantum gravity. And in fact, it's not an easy task in general to extract continuum physics from quantum gravity. So trying to go from this microscopic quantum gravity description to a macroscopic one. And we've seen that there are several obstacles when trying to go from one side to the other. A couple of them that are especially relevant for the context that I'm going to talk about are the localization problem that Bianca told us about, and the continuum, which is of course there for any background independent quantum gravity theory, but also the continuum limit problem, which is especially important for quantum gravity theories whose fundamental degrees of freedom are pre-geometric in nature. But there are still ways to address these problems. You could implement a relational strategy to address the localization problem, or you could perform some form of coarse graining to address the problem of the continuum limit, for instance, through some renormalization group analysis. But it is especially difficult to implement these strategies in full quantum gravity, both for conceptual and technical reasons. But Daniele showed us today that it is actually possible to do that in group field theory, at least in an effective sense, by choosing some appropriate collective states, which allow us to bridge between this microscopic description and the macroscopic one. So let me remind you very, very briefly how the whole strategy works. Let me remind you a couple of facts about these group field theories that also Andreas reminded us about. So first of all, the quantum group field theories are tetrahedra, can be seen as tetrahedra, which are decorated with discretized field data, and that could be gravitational field data, but also matter field data. And in particular, we will be interested in those, in particular in scalar fields in the following. And also the quantum gravity processes, so the process of these group field theories, can be seen as dual to discretized spacetime. So once you actually compute the partition function of the theory in terms of a sum over Feynman diagrams, what you obtain is a description of the simplicial gravity path integral. So the second step is the choice of states, and Daniele argued, and also Andreas, for condensate states. And they're particularly nice because they allow us to implement this notion of relationality effectively by picking the condensate wave function on the variables that we want to use as a physical reference frame. But they also allow us to implement the simplest form of coarse graining, as Andreas showed us, like this mean field approximation, so evaluating the partition function around the saddle point. And through this choice of states, one can then go to a macroscopic description, which is based on averages of collective observables and averages on these condensate states. And collective observables here in the context of group field theory can be translated as one-body operators in the group field theory Fock space. And then you can make contact with continuum physics, in particular with cosmological ones. And Daniele told us that the level of homogeneous and isotropic geometries, you have singularity resolution at early times under quite general conditions, and a classical limit at late times, which happens because essentially at those late times, the number of quanta in your condensate is quite large, and that suppresses all the quantum fluctuations that Andrea told us a couple of days ago. And you can also have a quantum geometric acceleration phase that could be associated to inflation or potential dark energy components. But here I'm going to instead move more towards the inhomogeneous side of the story, because of course there's a very rich physics that is related to these cosmological inhomogeneities, and most importantly, we have very precise observations of those. So it is particularly important to look at this. And I will show in this talk how to describe inhomogeneities from this full quantum gravity in the context, again, of group field theories, what kind of dynamics they satisfy, also compared to GR, and maybe if I have time, I will say a couple of words about how to extract the next steps that are going to be needed to go more towards observations. So let me start by describing the system that I have in mind, which is the simplest slightly relational inhomogeneous system, which is made of 4 minimally coupled masses and free scarf fields that we want to use as a physical reference frame, and one matter field, which is expected to be dominating the energy momentum budget of the universe, and which is slightly relational inhomogeneous with respect to our rods. At the quantum level, we have our group field theory, and this is going to be an EPRL-like model that we're going to consider, and we'll see that, oh, sorry, that was not supposed to happen. Oh, no. A lot of spoilers. Yeah. Okay. Okay. So you see that we have the group field theory field that depends on our gravitational variables and on our matter variables. And since we're considering EPRL-like model, these group field theory tetrahedra are space-like in nature. And this is a technical point, but it will become important in the following, so try to keep it in mind. One of the important ingredients of the description that I mentioned before were observables. And as I said, these are one-body operators in the group field theory Fock space. And you can have scarf field operators, so we can have frame operators and matter field operators. But of course, we would also have to look at geometric observables. And we've heard about the loop quantum gravity volume operator, and that can be translated into the group field theory context and turned into a collective observable as well. So we can look at this volume operator. But notice that restricting to volume information means that we're already restricting only to isotropic information, which is an important restriction, but allows us to make some step forwards. The second important ingredient are states. And as I said, we're focusing on condensate states, which are peaked around the values of our physical reference frame, which can be achieved if you assume that the condensate wave function factorizes into a peaking function, which is fixed, and a reduced wave function, which is instead dynamically determined. And here, a couple of more technical assumptions that the peaking function is supposed to be isotropic in the peaking of the rods, and the reduced condensate wave function instead is supposed to contain isotropic information with respect to this geometric data as something that is, and this is a constraint that is imposed at the level of the representation labels associated with these group variables. Then how do we describe inhomogeneities? Well, the simplest way in which we can do this is at the level of the reduced condensate wave function. So we assume that both its modulus and its phase split into a background part, which is only time dependent, and some small perturbations which are instead also rod dependent. And then you can run the mean field machinery to obtain some coupled equations for the modulus and the phase of the condensate wave function. And a late times, which is associated again to this having large number of quantity of condensate. Of course, at the background level, we find a matching with GR, where the macroscopic couplings are defined in terms of the group field theory ones. But at the level of perturbations, when we go in the deep superhorizon limits, so when the moment of these perturbations is very, very small, we have a perfect GR matching. But as soon as we turn these perturbations on, there's some unphysical and concerning behavior of these spatial derivative terms. And before I tell you how this problem can be solved, let me actually consider, instead of late times, let me consider early times. Because we've seen from what Daniele told us, that at early times it's where we have singularity resolution. So we do expect some fancy quantum gravity effects happening at early times. And we can still study this deep superhorizon limit, in which at late times we have the matching with GR. And looking at deep superhorizon modes is also particularly helpful because there's a way to systematically derive the equations for these perturbations in any modified gravity theory. And you can obtain the perturbations equations also by perturbing the background equation. So we were wondering if this is actually the case also for our group field theory emergent perturbation equations. And in fact, we found no matching with any modified gravity theory at early times. And we also find that our equations cannot be recovered by perturbing the background ones. So our interpretation of this mismatch is related to the fact that, in fact, when you follow either of these approaches, what you're perturbing is the metric. And that is an emergent quantity from the perspective of group field theory. In our case, our perturbations are at the level of the condensate wave function. These, in principle, are two variables. And what happens is that at late times, this phase variable is frozen and completely decoupled, while at early times it's dynamical, and it's particularly important for the dynamics of the modulus as well. So it's just a different set of degrees of freedom, and which might generate this kind of important mismatch. So finally, let me tell you about that unphysical behavior of spatial derivative terms, and let me specify what I mean with unphysical behavior. Because these spatial derivative terms don't behave as if they were spatial derivative terms with respect to minimally coupled masses and free rods. So we did realize that in order to better understand this issue, we needed a more concrete handle on the causal structure of these theories. So we consider instead an extended Barrett-Crane model where you have explicit access to the Lorentzian properties. And in particular, we consider the two-sector group field theory based on space-like and time-like iterator. And that also not only allows us to better couple these frame fields, but also allows us to look at different kind of condensate states. And let me tell you what this equation means. So we still have a space-like condensate, which is this term here. We also have now a time-like condensate, but these are our background quantities. So the condensate wave function is homogeneous relationally, and they're peaked because we want to implement this effective notion of relationality. However, perturbations now encode nearest neighbor in a relational sense to body correlations. We can have space-like space-like correlations, space-like and time-like correlations, and time-like and time-like correlations. So you can run the mean field machinery again. And what happens is that first of all, we have two mean field equations for three variables, which is not a good start. But what happens is that if you look at late times and you require that this physical behavior of the spatial derivative terms is satisfied, then this fixes the dynamical freedom completely. And you can actually look at the equations for the dynamics of this volume perturbation and the scalar field perturbations. And what happens is that there are quantum gravity corrections at relationally transplanckian scales, but there's GR matching at larger scales. And also let me mention that for some observables and for some specific solutions to the GFT equations, it's actually almost impossible to distinguish between GFT and GR results. Okay, so this is a brief summary of the story. Let me just emphasize what are the main results. And so the first is identification of these inhomogeneities as quantum correlations, which really goes towards the idea of having non-trivial geometries coming from quantum entanglement of the fundamental degrees of freedom. And we did find the dynamics for these perturbations, which is transplanckian relation, which has some quantum corrections in the transplanckian regime. And this quantum gravity emergent dynamics seems to differ from any modified gravity theory, possibly casting some doubts on the rewriting of these dynamics in terms of effective field theory in that regime. Yeah, and these are some steps that we would like to take in order to go more towards observations. So thank you very much.
Okay, thank you, Luca. Questions?
So this related to the morning talks. If you have inhomogeneities in well, trans-Planckian or close to Planckian, you can check if there's a consistent causal structure. Have you done that, or can you say anything about it?
What do you mean consistent causal structure precisely? Like if they satisfy some causality relations?
Well, you have evolution equations. Yeah,
Yeah.
if there's a
Yeah,
like, is it a standard wave equation?
it's
or
a
is
standard wave equation in the relational frame, though. I can actually show you the form of the equation. It's a little bit of. So this is for the comoving curvature, kind of the comoving curvature. This is another important thing. This is the relational comoving curvature, or a variable that really looks like that. We're missing one observable to actually turn it exactly into the comoving curvature. And this is the equation for the comoving curvature. The GR part will be this one, and this is the quantum gravity correction. So it's still the same kind of hyperbolic structure for the equation. And here there are some plots, and actually that's what I was telling you before, that depending on some initial conditions, for this observable, the mismatch between GR and Goofy theory is very, very small depending on the value of these initial conditions.
Okay, then let's thank Luca again. Okay, our next speaker is Mark Herzberg, who's going to tell us about general relativistic decoherence with applications to dark matter.
Okay, all right, so you can hear me? So first of all, thanks a lot to the organizers for this very nice conference. Okay, so this is work based on done with my PhD student, Itamar Alali, who will be a postdoc at Brown University later this year, and it's in these papers here. Okay, so first of all, by way of motivation, let's just remember that quantum sort of macroscopic cat-like states are very easy to emerge. Okay, so for example, if you had a billiard table here and you put the balls in a very classical state, as these authors checked, it turns out it takes only about like 15 or so scatterings, and the wave functions, the wave packets have spread to be the size of the whole board. So it's complete in some crazy quantum cat-like superposition with entanglement and so on. All right, but that situation we normally don't care about very much because, of course, the room is full of air molecules and they're just crashing into the board all the time, and they cause very rapid decoherence, and so effectively the state looks completely classical. But we should bear in mind that even in this room, this is trying to happen continuously. Okay, now what we thought about in this work, my idea was to double check that for something in the universe that may not experience these regular interactions to decohere rapidly. And most of the universe, as you know, is dark matter. And I'm particularly interested in light axions, which are kind of a favorite candidate for many people these days for the dark matter. Now, there have been many claims. It's kind of controversial whether they're right or not. I want to be sort of agnostic as to whether it's correct. But Sikivi and many other people have claimed that the axion itself, under its evolution, even just through gravitational interactions amongst the axion to other axions, causes the axion configuration to itself launch into some interesting quantum mechanical macroscopic state. Okay, so it went through some interesting cosmic history. This is, say, a cartoon of what we would expect the axion field to look like in, say, our halo today. So this part is completely uncontroversial, where let's say this is a typical de Broglie wavelength of the axion. Okay, that's what it should be. It should be order 1 fluctuations on the scale of its own de Broglie wavelength. And for light axions, that de Broglie wavelength is actually huge. It's macroscopic, like kilometers and beyond. That's what we expect. And it's plausible, however, that it's not just some classical field configuration, but actually there are quantum superpositions here. Like if I zoom in on this bit, maybe it looks something more like that. Now, in this case, our question was, if that is indeed the way it is, remember there's a big Hilbert space out there. We don't know a priori what state the dark matter landed in. Does it decohere? And at the very least, we know that gravity, dark matter, of course, experiences gravity. So gravity can cause decoherence of this thing, and we wanted to check how rapidly that happens. And furthermore, it's been claimed by Marsh recently that whether it's in this interesting quantum state or not has ramifications for direct detection experiments. Okay, so we can set up the problem as follows. Imagine you take a piece of the dark matter that somehow organized itself into some interesting cat-like state. So I'm going to represent the two parts of the superposition, the blue and the red, piece 1 and piece 2. You can imagine they're separated in terms of their center of mass, or they're separated, distinguished by their shape, or their phase, or so on. Or more generally, you can imagine some interesting entangled state if you divide up the dark matter into, say, half here, half there, plus some other combination. Okay, and now we're going to do kind of the opposite of the way we normally think about physics, where familiar particles, say like baryons, are going to be our probe particles, our environment, and we're not going to track them too carefully. Because these might be, say this is a piece of the dark matter floating in the galaxy, and then there's just some baryon or whatever that just passes through it, and we're not going to track that. So the initial state is a sort of product state, let's say, between the dark matter piece and this probe particle, say a baryon. And then, I keep going the wrong way, just gravity itself, at the very least, would cause this probe particle to scatter into a superposition depending on whether it interacted with the blue piece or the red piece, just from gravity. And so the final state is an entangled state. So you can write down the full density matrix, trace out your environment. In this case, let's call them baryons. And then the off-diagonal pieces, which in some sense control true quantum effects, are related to these overlaps psi2, psi1, where those are the overlaps between our scattered pieces here. So if the overlap between these two is small, the off-diagonal pieces are small, and we've kind of learnt what the state is, and we have decoherence. Okay, so of course we don't just have one baryon that would pass through. If you have some dark matter, there is a flux of particles moving through it all the time, trying to learn what state it's in. And so the off-diagonal pieces are related to essentially some product of the flux of particles. And if I denote the leading deviation from unity as delta, you can roughly exponentiate this thing and read off a decoherence rate. So the decoherence rate is related to the number density of our probe particles, their typical velocity as they pass through, let's say in the center of mass frame of the dark matter. And then there's some integral over impact parameter, and this perturbation delta, the deviation from unity. Okay, so first of all, these axions, if I imagine that the superposition is on the scale of its own de Broglie wavelength, dark matter has very low density. So the total mass contained in these regions is actually very small. And so the scattering is actually tiny, so you can work perturbatively. And so it's simple. So first of all, you just write down some standard scattering amplitude, a Fourier transform of the Newton potential established by each of these pieces phi. And then it's useful to define some kind of cross-section, which I call a generalized cross-section here, which depends on which piece you're scattering off, or there's some cross piece as well, F1, F2. And you can crank the handle and show that the decoherence rate looks very familiar. It almost looks like the standard N sigma V, which is the usual formula for a scattering rate, except it decomposes in terms of NV times sigma 1, 1. So that's the scattering cross-section of object 1 plus sigma 2, 2, scattering cross-section of object 2, and then there's some cross term, which doesn't have an ordinary interpretation. But this is just what you get from doing the perturbation theory. Of course, in the limit where these two objects were the same, this will all cancel out to give 0. There's nothing to decohere. But when these two objects are more and more separate, this is a bigger and bigger number. Okay, for the case of gravity, you can evaluate these things. There's some subtle about regularizing the forwards direction. but you can handle. And then the decoherence rate scales like this, where, for example, it depends on capital M1 and M2. So those are some characteristic masses of the superposition, mu1 and mu2, characteristic inverse sizes of the superposition, and so on. And then you can apply this to diffuse axions in the galaxy, as we expect them to be. Okay, so again, you could say the scale is set by the de Broglie wavelength, so that's just set by the axion mass and its velocity. But we know these velocities. We know that dark matter is moving at 10 to the minus 3 times the speed of light due to virialization. The characteristic mass in that region then is just controlled by the known local density of dark matter, which is like 0.3 GeV per centimeter cubed times that size cubed, and so forth. And then you can just compute the decoherence rate. And it scales like this. And you notice everything here we know except for the axion mass. Okay, and it has this incredibly strong sensitivity to the axion mass to this high power of 8. Okay, because again, the mass is controlling the size and the mass in this way. All right, so you can just plot this thing. So this is the decoherence time as a function of the axion mass, right? Everything we know, except for this one microscopic parameter. As a reference, this dashed line here is the current age of the universe, and the blue curve here is the decoherence time. Okay, so for axions we find less than about, with a mass of less than about 10 to the minus 6 eV down here, you have rapid decoherence. 4 minutes left, is that okay? On the one hand. On the other hand, if you're interested in experiments here on the Earth, this dark matter has to pass through the atmosphere of the Earth and hit your detector, where the number of scatterers is much larger, so the density of the baryons, of course, is much bigger, and that decreases the decoherence time from the blue curve down to this green curve, and then you find for axion masses less than about 10 to the minus 5 eV, it would decohere just from passing through our atmosphere, just from gravity. Just as a, now, what is this number 10 to the minus 5 eV? Is it at all interesting? So from this perspective, it's a complete coincidence that 10 to the minus 5 eV is actually in the order of magnitude of what's expected for the QCD axion, which, I mean, the scaling is completely different parameters. It just came out that way. So some of you may know that the typical density of axions has some interesting scaling like this. And for axions on the order of 10 to the minus 5 eV, you would get the right abundance in the standard cosmological scenarios. Okay, so that corresponds to a de Broglie wavelength of like a kilometer. So you can ask how much, let's put a further number on that, how much mass is actually contained in this little dark matter cloud? Well, again, the local density of dark matter is pathetically tiny, 0.3 GeV per centimeter cubed. That corresponds to a mass of like a nanogram or something. Okay, so it's this puny little thing with, it's big in space, but the actual mass is nanogram. If you go further to the left, right, the mass is getting bigger because these have giant de Broglie wavelengths, so there's much bigger mass there. Those are have bigger gravitational impacts, and they decohere rapidly. Way up the top here somewhere, it's long-lived, but it's kind of pathetic. It doesn't have much mass there at all. This mass is less than the Planck mass, which may make you not so shocked that it was, it can live relatively long. Okay, you can apply this reasoning to other more interesting objects like boson stars, which have a real gravitational impact, a serious one, and they just decohere like crazy, so they're completely classical. Now, it's fun, especially perhaps for this audience, to take a general relativistic extension of this analysis. So what I did so far was just Newtonian gravity. And let's imagine we treat the gravitational theory according to general relativity. So we have some superposition here. So now we can say it sets up a superposed space-time, g mu nu, that this particle scatters off. And we want to compute that. And we can justify this as gravity at these low energies is some kind of effective theory. All right, so it's well behaved, by the way. You might say, how do you do it? Because you may be confused. How do I think about a superposed space-time and all these questions? But it's actually well defined. You just pick your favorite gauge, such as Newtonian gauge. You have an asymptotic state that comes in from infinity, which is well defined, and you just crank the handle under the Hamiltonian and you get what you get, and you can compute the final overlap. Yep. Okay, so at leading order in perturbation theory, the scattering amplitude you can check just now is a Fourier transform of some linear combination, and the scattering rate picks up some correction here. And you can check that if the incoming particles are now photons, you can use this formula. So for example, there's lots of CMB photons that are trying to decohere this thing. But because the CMB photons have such little energy, it turns out that their rate of decoherence is smaller than the previous one from the baryons. Nevertheless, there is something fun to think about, which is a purely GR effect. So imagine every aspect of the superposition is just decohered away. But suppose my superposition, what's left is a superposition that looks like this, where the two parts have exactly the same spatial profile. So now Newtonian gravity cannot know the difference between these two. They differ by the axion's phase. So that's something that only general relativity knows about, because as the axion oscillates, it means there's a superposition in the local pressure and a superposition in the local metric as it oscillates, in fact. So you can have all sorts of fun computing this. You just take the four-dimensional Green's function. You have to deal with a source that has space and time dependence. It's a little more complicated. We did the analysis here. But let me just say the punchline is that you find that in this case, the rate at which you decohere the phase is actually extremely small. And that's related to there being some kinematic mismatch between the incoming and outgoing states. So to learn about phase, the scattering, so from this oscillation, has to be inelastic. And so it has to kick the incoming particle's energy to E plus or minus omega. That's the axion frequency. These are light axions. But on the other hand, simple kinematics tells you that the transfer momentum, up to some angle, scales like the ratio of the incoming energy to momentum times the axion frequency. And since the axion is non-relativistic, this is much bigger than the axion's momentum. Okay, so it somehow has to pick up this relatively large momentum kick compared to the axion's momentum. And since these amplitudes are related to Fourier transforms of the axion field itself, this is difficult to achieve. Okay, so in some sense, the decoherence of phase is especially slow. And this may have relevance to direct detection. Of course, after all, here on Earth, we need to detect this thing. And there, we try to make use of other higher dimension operators like phi FF dual, which are extremely small in the galaxy, but are just cranked up by orders and orders of magnitude here on Earth by laying down a big magnet. And so that's how you go after it. And those operators are all about checking on the axion's phase as it shakes your photon. Okay, so it would be nice if it's potentially observables related to this, though it's tough to go after it. First, we need to detect the axion. Okay, I think I'm out of time, but I'll just leave my conclusions up there. So thank you for listening.
Thanks, Mark. That was a fun talk. Questions? I had a few questions. The analysis that you did, it seemed like the fact that it was a scalar, it was not so important. You needed a small mass. Can you do a similar calculation, say, for a neutrino?
So, I mean, you could declare that this thing is a neutrino, but then the masses I would have you mean for the dark matter or the?
No, for the other.
For the probe particle.
Yeah.
So that's right. In that sense, since this is a gravitational calculation, leading order, the spin of the particle is irrelevant. So so here, for example, where I did the relativistic version, it doesn't matter. Your probe particle can certainly be a neutrino as well. But we checked, for example, CMB photons turn out to they have a much larger number density than the baryons, but their energies are so tiny that they're less relevant than the baryons that are passing by, and the same should be true for neutrinos. But yes, you can apply it to neutrinos too.
More questions? Well, if not, let's thank Mark again. Yes, so that was the last talk. So now we're going to move to the discussion. And I guess we should thank all the speakers from this session.
Oh, you already gave the. It's on? Okay. Okay. Welcome, everyone. We are still waiting for the last panelist because probably the other parallel session is a bit late. But yeah, so in the meantime, you can enjoy the last moments together with your friends. So.
So it doesn't need to be on record, thank you. No, it will take like 5 more minutes until we get started. So we are still missing one panelist and approximately 1/3 of the audience.
So I think, yeah. Okay, so I think it's time to get started. Welcome everyone again to this final discussion session. And before I just pass the words to the stars, let me just say that, well, first after this week of this live conference and in flesh and blood with many people that we didn't see for a long time, I hope that you enjoyed the diversity of the topics and the many beautiful talks we had. And I think it's my duty to make this public, which is So this conference was organized by, as you know, by people here in Nijmegen. But there was a driving force that, I mean, was unstoppable and made this conference happen in a rather short notice, which is Professor Frank. So, and I think, oh, sorry. Oh, I have to be here, okay.
Science, please.
Just one sentence more. So I think he went really beyond the ISQG, the International Society for Quantum Gravity, and he made a really great job for the quantum gravity community in general. And I hope that, well, I don't hope, I really felt that this must be emphasized very, very loudly to all of you. Okay, so during the week we collected some questions and from virtual participants, from you, and well, we had a nice collection of questions, but there was some overlap, and I tried to condense as much as possible all these questions in 4 questions, and I'm sure that we're not going to discuss the 4 questions, but I think I will start with the one that I selected as the first one, and the format will be the following. Every panelist will speak for about 2 minutes about their view on these questions, and then we open to the audience for comments and discussions. So the first question was a combination of 2 frequent questions that appear in the Google form, which was, in your view, what is the relevance of unitarity in the construction of a theory of quantum gravity? And in particular, what is the meaning of unitarity in the context of quantum gravity? And just a plus, which is very much related, I think, what is the relevance, if any, of solving the so-called black hole paradox, so the information loss paradox, for our understanding of quantum gravity? So with that, I shut up and give the words to the panelists. So, is there any order that we should respect? Okay, let's do left right. Okay, so Jan.
Yeah, those are all very interesting and complicated questions. For me, what's important is that I think a minimal ingredient for quantum gravity is that semi-classical gravity emerges in a suitable limit. That is described by the usual action and everything. And the minimal approach to that is that it's just some sort of low energy effective action. We can be somewhat agnostic what happens at high energies, but it's supposed to be a very good low energy effective action even at the perturbative level. So all the notions of unitarity and locality and so on that apply to perturbative low energy effective field theory should come out of any approach, I think. Whether or not there is a notion of unitarity in a full non-perturbative completion is a much more confusing question. Because maybe it's trivial, like if you just take the Wheeler-DeWitt equation as it stands, it says that A psi equals 0. That means there is no time evolution, and in particular there is no interesting notion of unitarity whatsoever. If you look at the ADS-CFT, where you have a boundary, then unitarity is sort of built in, because the boundary field theory is unitary. So it really might depend a lot on the precise setup, what actually the non-perturbative version of the question is. But at a minimum, I would say it's a very important thing is that all the unitarity properties of perturbative gravity should be reproduced by any approach at low energies.
Yeah, I guess Jan got it covered. That's too easy. So indeed, I'm coming from the fully non-perturbative approach. For me, then the question is unitarity does assume some time evolution, but I don't usually know what is a notion of time. And so if I don't have a notion of time, how can I define unitarity? But of course, I want to reconstruct unitarity in the low energy limit, in situation where I can have a good time, in situations, for instance, in which I'm asymptotically flat, or have a boundary. In addition, there's kind of two recent questions which you can consider. One thing is if you do have if you do believe in some kind of fundamental discreteness, but we also do have an expanding universe, you might ask how that goes together. And Philip Höhn and myself have developed such a formalism, but also recently have been a paper by Strominger and Kotler about weakening unitarity. It becomes even more paradox if you think of collapsing universes and lots of information. So there's this thing. The other thing which I'm reported in my talk is these complex terms in the action for topology change. So if one thinks about topology change and third quantization, which Daniele spoke about, it's also lots of questions for me. What does unitarity mean in this context? And for what do we need it? I mean, usually we need it for probability interpretation, and there are some frameworks which try to generalize this probability interpretation and to have generalized quantum mechanics. So it's also kind of a question, do you want to reproduce exactly the quantum mechanics, or do you expect some modification of quantum mechanics from quantum gravity?
Partial coverage, but let me add my own point of view, which comes from also very much informed by non-perturbative theory, where we're working in a framework where one can, we have some quantitative understanding already of mechanisms of emergence of anything, which I would say these are the kind of the basic principles. I mean, I wouldn't just name unitarity, but also locality and causality, which I would say people, of course, say, oh, anything goes at the Planck scale. But then, of course, it has to be regained, or to use a more popular term, it has to re-emerge. And things typically just do not emerge, because by what mechanism you have to ask? I mean, wishful thinking alone is not enough. You know, you have to come up, even, you know, try it in toy models, this is very difficult. So you abandon these principles at your peril. So if at any lower energy, you know, even be just where gravity is completely switched off, of course, I mean, unitarity is very much built into how we think about, you know, standard quantum field theory. So I think, so that's point number one. So as a corollary, anyone who loves and strongly believes in Euclidean, you know, in Euclidean quantum gravity also has to explain where, well, how does time, you know, re-emerge? And therefore, how can I even start asking questions about unitarity and causality? To the issue of, oh, you know, part of my heart is canonical, so, oh, there is this problem of time, and which time should I choose? I would say, well, choose a time and show with respect to that time, make it natural, make it proper time, make it cosmological proper time, or, you know, something that's not just some coordinate time you picked out from, you know, an infinity of possibility, and show unitarity there. I think we know that it's asking too much to have all time reparameterizations unitarily represented in some non-perturbative theory of quantum gravity. I think this is wild. So try and make things unitary. Of course, there are hard questions when you come to cosmology, but I'm just talking in the sense of more, well, quantum gravity, after all, is something like a local quantum field theory, hopefully.
Okay. Well, I'm a student of Bryce DeWitt's, and Bryce always said that you should push what you know as far as you can to see where it breaks rather than throwing it away. So I'm reluctant to throw away something that seems to be a very fundamental part of quantum theory as we now understand it. That being said, though, unitarity, as other people have said, refers to time, and in order to say whether it makes sense in quantum gravity, you'll have to tell me what you mean by time. In settings where, like ADS-CFT, where there is a clearly defined boundary time without quantum difficulties, then I think unitarity is very natural in terms of boundary time. Though even there, it's not clear what bulk unitarity means. In a more general setting, if you want to use some kind of relational time, you would have to tell me what that time is. Is it, even classically, is it defined globally? Is it defined for every manifold that you might want to include in a path integral? If you can give me a relational time like that, then I would expect something like unitarity, or at least that would be my first guess. I don't know that such a time exists.
Okay, I think unitarity and the question of black hole information, really are together key questions in the field, so much so I suggested a more substantial discussion on it. Maybe whoever organizes the next quantum gravity might go more in that direction. The reason is as follows, without a complete discussion. If we consider the alternatives, some form of non-unitary evolution, we typically land on a disaster, basically. It doesn't work. On the other hand, if we try to preserve unitarity in the black hole context, we get strong indications of new non-local behavior of quantum gravity. So it seems to be telling us something. And that's why some of us view this as a key problem for quantum gravity. So without going into all the details of that, let me just mention one other point, and I think it's also sociologically important in the context of black holes, because we can talk about one or the other formalism of gravity and what's better about it, et cetera, but really focusing on what different formalisms have to say about specific physical phenomena, Gedanken experiments and so on, gives us an opportunity for more concrete dialogue between different ways of looking at things. So those are at least two of the reasons. And finally, regarding whether unitarity is sharply formulated, I agree when you try to think about, say, finite time evolution, there are various subtleties. But one sharp way to think about it is if the theory of quantum gravity has states which behave like asymptotically flat space, Minkowski space, then you can think about the S matrix and ask about unitarity of the S matrix. Of course, you have to deal with subtleties of infrared issues, but there very much you can make it a sharper question. So that's it.
Thank you very much. So now we open the discussion to the audience. So I expect that some of you would like to kick off either asking the panelists or raising another concern about unitarity. Okay.
Thanks. As a former quantum fundamentalist, I'll try to maintain two contradictory ideas at the same time. I believe that unitarity is important, and it was covered, as we say here. On the other hand, I'm not sure that information loss problem and unitarity in the context of black hole evolution is a really significant issue. It's very useful in prompting people to think about a number of topics, and I think some of them are very important. But if you say, from the standard of formulation of standard quantum paradox, if we try to formulate what goes into clean formulation of information loss problem, we end up with a list of important questions, particularly about nature of degrees of freedom of a gravitational field and how it translates into quantum domain and whether they're local or not. But we are far from clean formulation of information loss problem. So in a sense, I don't believe it's a problem. there is a long list of things that need to be precisely defined for us to honestly declare that we have a problem. But unitarity is important, and whether it's true or not, above my pay scale, but it's interesting and useful tool.
Okay, perhaps, yeah, should alternate, otherwise.
So, I mean, one question to me is always, given that unitarity sort of breaks down in every single measurement, why should we believe that it holds as a fundamental assumption in large, like in the theory describing the whole universe? So, like in my point of view, it's sort of like the worst assumption in fundamental physics because it's violated in every measurement, and the connected question would then be, can we solve quantum gravity without solving the measurement problem?
Do the panelists want to say something about that?
The statement that it's violated in every measurement depends on a particular view of what a measurement is, and so I don't think that's a fair statement. If we think about the full quantum evolution of the universe and observers in the universe as quantum systems, then that's not really how we look at it, and say decoherent histories or something. And again, regarding the sharp formulation, one reason why we can think about it, this comes back to the first question, or why we should think about it, say, in terms of the S matrix, is there we have a kind of clean formulation. In terms of asymptotic states, we think we understand, ordinary particle states coming in or boosted versions of those, going to ordinary particle states going out. And you can cleanly formulate it, again, modulo some IR subtleties in that framework. And then you have a leading semi-classical contribution to those processes in the ultra-high energy regime. And based on Hawking's analysis, that leads to a disaster, a huge amount of missing information. And so, I think when you look carefully at what goes into it, there are not so many subtleties as were just alluded to.
Okay, this is just to spark more discussion on this issue. We could go for longer, probably. I didn't like this way of starting, saying that once you give up unitarity, everything is a disaster. Why? Because it disqualifies every possibility before giving any reasons. In a sense, for me, in a quantum gravity conference where we are talking about space-time things, it's a little bit disconcerting that we are talking about an issue that when we want to ground it, we have to say about things about the S matrix, where things evolve only in time. So in a sense, we want to make things space-time local, and they're talking about unitarity as a building block is very restrictive. So I don't want to claim I have answers, but I'm saying that if we put it in as a requirement, we are tied to something very, very strict. I like much more the point of view that it has to be recovered somehow in certain limits, and to, for example, when we analyze the S matrix, yes, it makes sense, and there is something we have we have a reference, and we can say we want to conserve probability with respect to that thing. But in some other aspects of what we want to talk, we have a local theory, and we can say we want to preserve probabilities of certain things with respect to certain other things. And anyway, that's my point of view, just to spark more discussion.
Hi, just to give an answer to the question of that guy. Well, I'm not a specialized people, but there are some groups, especially in my university, that they think that actually we cannot solve the problem of quantum gravity if we do not solve the problem of the measurement problem in quantum mechanics. They believe that these two things are very strongly connected. So actually they have some words where they relate the measurement problem with the information loss paradox. So, and in some sense, I agree with them that we need to be more careful, especially when we talk in some technical aspects of our approaches. It is important to, yes, to clarify that technical aspects, but it's also important to clarify some conceptual things like this one, because if we are not able to clarify that questions, we will be in trouble because maybe we are doing something that is not right. So it could be very important to clarify these kind of questions. And answering to the question of this guy, there are some people that believe that no, we cannot solve the problem of quantum gravity without solving the measurement problem. So there are other perspectives, but I actually agree with them. But answering the question, well, there are people that believe that no, we can't.
Okay, so just to organize a little bit, so Sumati has a comment, and Bianca has a comment, and then we move to other topic. Okay.
This is just to add my two paisa to the discussion, which is that it seems that the broader context of unitarity has to do with probability conservation. And the question within any quantum formulation of quantum gravity, if you think of that as a way to think of unitarity, maybe there are formulations in which we're not talking about evolution being unitary, but that in some broader sense, say in a history's perspective, where you can think of the decoherence functional or the coherence functional, whichever way you like to call it, as giving you a normalization, telling you that in some broad sense, quantum probabilities are preserved. So and in that way of thinking about it, you don't really need a way, you don't need a time, you don't need an evolution, you don't need the sort of local definition of unitarity. So I'm just suggesting that there could be broader conceptions of our understanding of unitarity, which are based more on a history's perspective.
Bianca?
Well, to be on a more reconciliatory note, I think, well, I do think many of us spoke in a global context. We don't know what the notion of time is, what unitarity is, and Steve was talking about more local things and high energy scattering. And there I do think it's a very important question of what happens in a high energy scattering, where you can have a time asymptotically, and whether black holes form and whether everything is consistent, and it's a question about the stability of even flat space to understand these processes. And I would like indeed to know in the various approaches what the answer is to have ultra-Planckian scattering, whether these are unitary processes or not. I do think that would have been important consequences. So there's probably two different kinds of answer depending on what kind of processes you consider.
Okay, thank you. So, as I said, we don't have time for all the questions, so I will merge two questions. And the second question is, what are the most promising avenues for experimental hints in quantum gravity? So what or where we should focus our efforts? And merging to the other question, is local Lorentz invariance a potential candidate to be looked at? So now I pass to the... No, so yeah, so it's a question about experimental hints of quantum gravity, and if you have something to add about local Lorentz invariance, that would be good. Okay, so Jan can start.
That's not fair, huh?
Ah, okay, okay. So you want to? Okay, that's fair enough. Okay.
Okay, for regarding local Lorentz invariance, I bring a standard complaint, which is I don't know what local Lorentz invariance is. So if I try to define it, it's for me a version of diffuse symmetry, and so diffuse symmetry I find very important. But then it's a question, indeed, how does it influence the propagation of matter? Well, I would like to have that in a background independent and ideally diffuse symmetric way as far as it's possible. But I can imagine that there's kind of something like a deformation of Lorentz symmetry happening. Regarding promising avenues for phenomenology, I do find currently very interesting these new considerations on basically gravity-matter interactions. That goes a bit also, relates to the swampland, to consider what kind of matter couplings and behavior we can predict or post-dict from the consistency of quantum gravity. And that seems to be, for me, indeed, promising to give lots of restrictions on our quantum gravity theory as far as we can compute it.
Okay, question number one. Yeah, so the local Lorentz, yeah, I agree with Bianca. I think we agree on the same point. If you are in a really non-perturbative regime where there is no G mu nu, even in an approximate sense, there is just no operational way to talk about the action of the local Lorentz group. So that question only makes sense, let's say, for anyone who works with some discrete models or something like DTs or others where there is no, not even, as I said, in some approximate way, a G mu nu to talk about, where or a local patch of your geometry where to some approximation it looks like a piece of Minkowski space, and then I can start talking about rotation. So I don't think it's like diffuse for me, but it's something like, of course tangent space doesn't exist if you don't have tensor calculus, but if you have can approximate your patch by something that looks Minkowski, and then you can start talking about this. Is an important question. Again, how will that emerge? It's part of emergence of space-time structure, I would say, coming from a very non-perturbative point of view. So it's an interesting question. In terms of where can we make contact with cosmology, again, I'm slightly biased by my own constructions and point of view, where we find from CDT an emergent space-time that has some de Sitter properties. So the very obvious thing is to compare it to early universe cosmology, where everyone else takes a nice, perfectly symmetric de Sitter space as their preferred vacuum state, if you like. So the question is really, can we derive this from first principles, and can we confirm, for instance, by studying two-point functions, that's something it's coming within grasp of what we can do, assumptions that are being made and kind of pulled out of the head, which are the starting point for standard cosmology. And of course, the magnifying glass we have is then inflation that comes after, doing whatever our perturbations are then, coming perhaps from an underlying quantum theory.
Okay. So first of all, when quantum gravitational phenomenologists talk about local Lorentz invariance, I don't think they mean what mathematical relativists mean by local Lorentz invariance. I think they mean Lorentz invariance over macroscopic, large macroscopic scales, scales small enough that the universe is approximately flat, but much larger than what we mean by local Lorentz invariance as a gauge invariance of the tetrad. I think it's worth looking. I would not bet any amount of money that violations of Lorentz invariance are going to be found anytime soon. For promising experiments, well, I'm very excited by these upcoming, maybe 10 years from now, tabletop experiments to see whether entanglement of positions of Planck or larger mass induce entanglements of gravitational fields, because it would be nice to have some actual observational evidence that gravity is quantized. But it would also be totally shocking if any result came out that wasn't what we all expect. I don't know what else is a promising experimental avenue. I think we have to look all over the place. As I said this morning in preparing a review about causal structures in quantum gravity, I realized that this may be my own ignorance, but I don't think that enough attention maybe has been paid to the question of whether even Planck scale fluctuations of causal structure might be observable. But I leave that as an open question.
Okay, I guess I'll address the more formal notion of Lorentz invariance. And if quantum gravity does have a state that behaves like the Minkowski vacuum and excitations about that, then it seems to me that Lorentz invariance itself is a key property in that context and is pretty well tested in sort of this large radius limit as compared to the Planck scale. But then locality is a little more puzzling. So the extent to which we have locality, we will have local Lorentz invariance perhaps, but locality in my mind is in question, how to think about that sharply in gravity. And so possibly modifications to locality are a key point here. My own view is that the underlying structure is quite possibly not the geometry of a manifold, and so in a way it's not even the right question, or it's not the right way of going at it. On the experimental end, I guess one could also mention new tests using interferometers, which are more lab-based. That's one possibility. But I also think we should really consider quite thoroughly that we're now observing strong gravity regimes near black holes 2 new ways, right, in the past few years. And moreover, this problem of information loss, this severe problem of unitarity is suggesting that there is, in my mind, quite likely some new phenomenon taking place in that regime at scales of order of the event horizon radius. And I think, in fact, that's in some sense emerged as a consensus of the field, or some part of the field who thinks about this. There have been various proposals for what the new physics is on event horizon scales, but modulo the fact there are different proposals, the consensus is that there is something novel there. And so we should really try to think hard about whether that can be seen via gravitational wave observations or, of course, the more electromagnetic-based observations like with Event Horizon Telescope.
Very good. So as far as local Lorentz invariance goes, I don't have much original to say because I was also confused what it means. If it means the equivalence principle holds locally and so on, then my answer would be the same as for unitarity. We think that perturbative gravity should emerge, and to the extent that that has local Lorentz invariance, it should come out in that way. Any more drastic modification where you by hand, imagine adding a term that explicitly breaks general covariance in an effective field theory, seems to me theoretically poorly motivated at this moment in time. As far as experimental things go, that's obviously a super important question. I think this idea of trying to see whether UV completability of a low energy theory in the spirit of the swampland program puts bounds on coupling constants, as Bianca was mentioning, is a nice thing to explore. Perhaps looking at density fluctuations in the early universe will shed some light. There's some extra data coming up about what the initial conditions of the universe were. And there might be various ways to try to connect that to quantum gravity somehow. For example, if you think the initial state of the universe was related to some version of a no boundary proposal, then different choices of, say, no boundary proposals or complex contours that you choose for early times might have different imprints on density fluctuations. I kind of sort of intuitively feel that the fact that black holes, when you increase their energy, they also increase in size, is a weird thing, because normally if you increase the energy, you go to shorter distances, not longer distances. This is sometimes referred to as UV-IR mixing. So there might be some connection between physics at very large distances and physics at very short distances. And so it's conceivable that maybe some sort of quantum gravity phenomena that you might naively think operate at the Planck scale, by some sort of UV-IR mixing have very interesting, very long distance effects as well. But I don't think we know precisely how to look for those, but it's an interesting thought. I also think it's maybe, like if you think about, say, Aegis CFT, it's interesting to see whether you can just put these CFTs on a computer, or as was recently tried, put some qubits in a lab and try to sort of see if you can engineer quantum, things like quantum wormholes and so on. I mean, this is a very contentious result. But as a general direction to see if this is a way to sort of do quantum gravity in the lab in an indirect way, I think it's also a fun thing to try to do. It's maybe not directly testing quantum gravity in our universe, but it does test in some way some conceptual foundations of quantum gravity. That's it.
So now we move to the audience, and yeah, comments, questions. Claudio? Okay, so let me give a chance to someone else.
Okay, I just wanted to make a technical comment, a short technical comment regarding this thing about local Lorentz invariance. If you remember the history of GR, general relativity, there was this argument presented by Eric Kretschmann about diffeomorphism invariance of the theory, where he basically said that any theory can be rewritten in a manifestly covariant way, right? So this is the effect of diffeomorphism invariance is really not a physical requirement that you can put on the theory. So the same thing can actually applies to any symmetry. So you can rewrite the Schrödinger equation in a manifestly Lorentz invariant form. So the only issue is that once you do that, sometimes you have to introduce some background fields to compensate for the transformation laws and so on. So basically what is being done when you say that some symmetry is being broken, what you're actually doing is breaking background independence. So symmetry as such is a matter of convenience of our equations. And background independence is the thing that has content that the physical theory does or does not satisfy. So breaking of Lorentz invariance is actually breaking one specific form of background independence. So.
Okay, thank you.
Am I allowed?
Of course.
Okay, then I would like to pick up on the perspective taken by Jan. So, because this is something where the functional randomization group was able to say something. So you start with something that is diffeomorphism invariant. You add an operator that is non-diffeomorphism invariant at high energies. You try to go to low energies, and then the result was it's not natural that the difference actually vanishes. So I think Benjamin Knorr has a very catchy paper with the title Lorentz Symmetry is Relevant, and this summarizes our take on this question.
Thank you. So, more comments, questions, concerns?
So everybody has been very politically correct, which is good. So that is worth it, and this is worth it. So put a little spice. So what is not worth it?
So I think Claudio wants to make a comment, and
sorry,
up there.
So regarding local Lorentz invariances, so I mean there is this recent claim by the VIP collaboration. They are testing the Pauli exclusion principle, and they claim to rule out theta Poincaré violations to order Planck length squared. So any theory basically that requires that is, according to their claim, dead. And I think it does make, you can ask the question of local Lorentz symmetry if your fundamental description comes with an internal space of your degrees of freedom.
Oh, Sumati, yeah. So I see some repetition of faces in the discussion, so we should try.
Just, I mean, in this sort of experiments that have been proposed, there was this question of non-locality as well. I think Stefano Liberati at some point was proposing that there would be tests of non-locality, because that's another feature of quantum gravity that people have talked about. So I don't know this, what is the status of experiments in testing non-locality, I mean, causality preservation without, so not violating causality, but maybe having non-local effects, which can only be explained through a quantum theory of gravity. So I don't know the status of such experiments. If anyone knows, that would be interesting.
If people want to answer to that, otherwise I have another. I just want to add a comment, maybe reinforce something that Jan was saying about UV-IR mixing. Maybe, so my view there is that I think we have to be a bit honest that if you're doing quantum gravity, and if, let's say, Wilsonian decoupling is really at play, then, we are at risk of talking about something which is totally inobservable. So I think as a community, we do have to face that. For me, the only, and I may be wrong, but my view on that is that the only other option is that our theory of quantum gravity, needs to develop a phenomenology which is akin to this UV-IR mixing. So now I think the challenge for us, so maybe you could challenge me on that, and if people have quantum gravity observable, which are, by that I mean, effective theory is enough. If you have Wilsonian decoupling, I have effective theory, I put a cutoff, my observation is Planckian, we're done. So now I have my own, reasons to believe UV-IR mixing, but in fact, I think it's a challenge for us building models in quantum gravity to kind of see, is there a route? Is there some mechanism like that in the theory we're constructing or not? Or are we proving Wilsonian decoupling? So maybe I'd like to have, reactions on the panel or on the audience, like, where, why our quantum gravity model will be Wilsonian decoupled or UV-IR mixed. And if they are not, why are we continuing to work on it?
Yeah, just. So, do you want to comment on that?
I could try.
Yeah, and then Aaron has a comment. Yeah.
So, yeah, I could try. I hope I've understood the question properly, but I think the universe has performed scattering experiments that are very much like ultra-Planckian scattering experiments, but instead involving large particle number. And those scattering experiments have yielded some of these things that we're talking about that manifest UV-IR mixing, namely black holes, and very big ones. So, and if we have a complete quantum description of the universe, we'd better give a complete quantum description of those things, basically. So I think it's unavoidable now that we enter this regime if we want a complete theory where we explain quantum evolution of black holes. They're out there, we found them, and you could just as well make them in very high energy scattering experiments in principle if we could perform such experiments. So I'm not sure, does that address your question, or is there some other aspect of it?
Yeah, part of it, that you're saying, yeah, I agree with you that.
So this was unexpected.
But yeah, I'd love to hear from other perspectives.
Just say a few words, and then Aaron takes over, and yeah.
So I don't want to monopolize. I'm happy to hear more perspective on how you. Oh, you don't have a microphone. Yeah.
Yeah.
The theories.
I'll bring them back. But okay, you just wanted. Okay. Okay. I think Aaron wants to say something, and then Bianca say something. Yeah. I didn't know. Yes, sorry.
Yeah, so I agree with Steve that, for instance, the scattering experiments would be very important to know the answer to. The other is that also if I think non-perturbatively, I have difficulties to defining or deciding what is UV and what is infrared. And as an example, there's this kind of spike, for instance, very spiky configurations, or if you want to have it more drastically, the baby universes, which can have very small diameter and in this sense be UV, but on the other hand, can extend to very large distances. And so that would be part of understanding kind of these phenomena, which are a bit counterintuitive if you are doing standard quantum field theory.
Okay, one comment on maybe terminology to Laurent. I mean, if you call anything that's beyond what we can describe as effective field theory, UV-IR mixing, I think everyone would agree that that's something we certainly hope for. I mean, obviously we are hoping for quantum gravity signatures, well, which we wouldn't even probably think about if we just stuck to our effective quantum field theories. So that's one thing. Another comment is, I think many people now talking about, well, conceptual questions and conceptual problems and contradictions as being the real, difficult thing we have to address first. I think that's getting stuff the other way around. I mean, this is what's been happening in quantum gravity for the last 40 years, that people have talked about and argued about these conceptual questions, by which they oftentimes mean certain properties of elements in their preferred way to construct or think about quantum gravity. And I think quite a few of those will go away if we focus more on, hey, what is actually now, say maybe even in principle, the operational setup, I would use to show that there's actually a physical effect there. Many of those will go away. So, and of course, one can speculate which those includes. But I think that's a healthier way to go. And I hope also we as a community, we are now more focusing in part, as I was also saying yesterday, triggered by, well, data that are coming in, focusing more on this problem-oriented, operationally, what does it mean? Is there actually, there may be a contradiction between my and your formalism, because what I'm talking about is totally ill-defined in your, or conceptually, one cannot even talk about in your formalism, but we may still agree or disagree on the outcome of a certain experiment.
Thanks. I just wanted to comment on what Laurent said about effective field theory, because so first of all, I agree with you. I think that's a possibility that we face and that we should acknowledge, especially to the outside community, that it's a possibility that there's just nothing non-local happening in quantum gravity. But that said, I think there still is some sense of phenomenology, namely, this was alluded already to, consistency with all that effective field theory is something very non-trivial. And I think many approaches have a handle on that, but no approach has a complete picture of that. And I think that should be pushed. And then even in that framework, there's the possibility of a somewhat less exciting phenomenology that can even predict things, right? Because there is some ununderstood stuff even in the effective field theory of our universe. There are open questions, and in the end, in a long way, I think we have something to say about that.
Okay, so I'm quite amazed that after a week of conference, at very last slot is a discussion session, and we still have energy to discuss. But I think in order to, boost a little bit this energy, we should go for coffee. But before we go, Frank wants to say something. But just before Frank speaks, I think we should thank the panelists for the very nice discussion. Over there.
Oh. Thanks. Yes, can I go to the slides? So I had the pleasure to make a few closing remarks to this conference. No worries, I will stick to the 5 minutes mark. So let me see. Yes. So picking up the analogies of scientists' fish that we have here, I created a quantum gravity island. And this reflects about my personalized view on the field. So our task is to actually explore this island. So what the island is populated by are many rooted trees with marked nodes. And what we typically do is we live in one of these marked nodes, and we want to explore what's going on there. Now I want to thank all the participants of this conference and the plenary speakers and the parallel sessions to give us a scenic view about their particular node on this island. So I think for the community it's incredibly instructive to see and learn what is going on in other parts of your island, in order to be able to chart what are the possibilities. Now, you don't organize such a conference alone. So first I want to acknowledge our financial support. So there were many people contributing. I want to highlight the financial support by Daniele Oriti, so this is the DFG, and also the financial support provided by the Delta Institute and the ERC grant from Jan de Boer, so that makes the conference really a national initiative. And I would have bet my money that something like that would never have happened, but you proved me wrong. So I'm very happy about being wrong about this one. And then there was a huge team being here, organizing everything in the conference. Packing boxes, so that happened before. Then we had a welcome team guiding you here through the College Saal. We had a crew that helped up setting up the posters for the poster session. Maximilian and Jan manned the info desk in the morning for people who registered on Tuesday to Friday. And a particular thanks goes to the audiovisual team, which really made an amazing effort that you could enjoy this conference in a hybrid format. So thanks to all of you on this team.
Now I have to say, this is only part 1, so I couldn't fit all names on one slide. There are many more. So for our outreach, we also had a team which was guided by Beatrice Bonga. So there was the Science Café on Tuesday evening. This is Eric Stoffels and Femke Verhout. The Study Association organized the walk-in moments for the bachelor students and the master students. So this was Matthijs Lau and his friends. And we had very good outreach speakers talking to the general public and our students here. So also there, a great thank you for all of you. Yeah. And by now everybody has met our secretaries, so they also had a great influence on the success of this conference. Now, in the background, we had a scientific advisory committee. The names are on our website. My apologies if not all wishes of the scientific advisory committee were granted in the program. It was impossible to have all contributions here on stage, unfortunately. Then the International Society, which is running this series of conferences. The Young International Society for having an afternoon session dedicated to PhD students, so I hope that was also very helpful. And then our local organizing committee, Beatrice Bonga, Timothy Butt, Badri Krishnan, Renate Loll, Antonio Pereira. So thank you to all of you. We are still friends after this initiative. Yes, and then of course, the organizing committee stops now, and we are very much looking forward for someone stepping forward to organize Quantum Gravity 2025. So if you are interested in doing so, please raise your hand now, or contact the International Society saying, yes, we are up to this task. So for us, it was a great fun having all of you here on campus, and we all hope that you have a safe journey home, and there will still be coffee in the Science Café where you can say goodbye to your friends. Thank you to everyone.
And just a final remark, we have a lot of quantum gravity posters still hanging around, so if you'd like to take one as a souvenir, be our guest.